Hi everybody. In this video lecture, we are going to talk about solubility equilibria. Yes. All right. We've previously learned all about solubility and the factors that affect solubility. So just as a reminder, your definition of solubility is the maximum amount of solute that will dissolve in water. So the amount of stuff that you can get dissolved in water before nothing else will dissolve in water. Instead, you'll just have stuff starting to pile up at the bottom. So by definition, at equilibrium, there will be no excess solid remaining. You will not have anything piled up at the bottom. It's just the maximum amount of stuff you can have dissolved with nothing else showing up at the bottom. So by definition, at equilibrium, the concentration of your salt should be equal to 0. So let's see what that looks like in the form of a problem. Let's put some numbers in it. So let's say that the solubility for the salt silver bromide is 8.8 times 10 to the negative 7th moles per liter. We want to figure out KSP from this. So first things first, let's remind ourselves, what is KSP again? So K tells us that we're dealing with some sort of equilibrium. These little subscripts down at the bottom, really what they're there to tell you is just what type of equilibrium are you dealing with. So this tells us we're dealing with a solubility equilibrium. SP stands for solubility product. So this tells us we're just dealing with equilibrium and we're talking about solubility equilibrium. All right, so the initial concentration of our silver bromide. What we're saying is we dump in 8.8 times 10 to the negative 7 moles in 1 liter of water. So at the beginning, that's our concentration. Before anything has started to dissolve, we won't have any ions present. But we know from the definition at equilibrium, this salt is going to become a concentration of 0. We will have none of the salt left. All of it's going to go into solution. So from here, we can figure out our change. If we start with 8.8 times 10 to the negative 7th moles per liter, we're going to end up with 0. Our change is negative 8.8 times 10 to the negative 7th moles per liter. So what that means is if this is our change and everything's in a 1-to-1 ratio, we're going to get the same thing over here, but instead we're adding it. We're going to increase ion concentration as we decrease concentration of our salt. Both of these are in a 1-to-1 ratio with the salt, so that means that their change is going to be equal to 8.8 times 10 to the negative 7th, which means that equilibrium will have 8.8 times 10 to the negative 7th moles per liter. So this tells us our equilibrium concentrations. And now what we're going to do from this is determine KSP. So we know that our solubility product is equal to the concentration of just our ions in solution. Remember that when you write equilibrium constants, it's always KEQ is equal to concentration of your products over concentration of your reactants. But we never include things that are solid or liquid. And our reactants are always designed to be the solid because we write our dissolution reactions going from solid to the aqueous ions. So in this case, we'll never have any reactants to worry about, which is why KSP is always just equal to concentration of our products. So our products here are silver ion, Ag+, and the bromide ion, Br-. We don't have any coefficients, so both of these are raised to the power of 1, so this is our solubility product. To find the value of it, what we're going to do is plug in our equilibrium concentrations. So at equilibrium, we know that each of these things has a concentration of 8.8 times 10 to the negative 7th molar. Rather than plugging this in twice, I know that I'm just essentially squaring this value or multiplying it by 2, so I'm going to write my solubility product like this. But really what we're doing is 8.8 times 10 to the negative 7th times 8.8 times 10 to the negative 7th. So plugging this in your calculator will yield the value 7.7 times 10 to the negative 13th. So this is our KSP value for this reaction. Okay, so our practice problem, what we can do to practice this skill is take iron 2 hydroxide. Knowing its solubility is 1.4 times 10 to the negative third grams per liter, we can find KSP. But keep in mind, KSP is always about concentrations, right? And what's the units for concentration? What are the units for molarity? Moles per liter. So always pay attention to your units, because this is where you'll get tripped up. Here our units are grams per liter. So before we can do anything else, what we have to set up is the right units. So if I know that we have 1.4 times 10 to the negative third grams per 1 liter, how can I get to units of molarity, moles per liter? I have to plug in molar mass. So in 1 mole, what's the mass of iron 2 hydroxide? So this is something that you know how to do, so I'm going to let you pick up the problem right here. Put in your molar mass there, figure out what your molarity is, and then you're going to go through the exact same steps that we did in the example problem to get your KSP value. So try that out, check in with the answer key, and then come on back for the next section. All right, so the next thing that we are going to want to be able to do is determine your ion concentrations. And we're going to start out with soluble salts because they're easier. Why not? So soluble salts, to be soluble, it means that you dissociate completely. All of your salt dissolves into your ion forms. So how can we find concentration of each ion? It's actually fairly simple. All we have to do is take the concentration of the solution and we multiply it by the coefficient for each ion. So here's our example. Determine the concentration of each ion in a 0.10 molar solution of aluminum sulfate. So knowing that I obviously set these things up to give you an example under each category, we're going to know that aluminum sulfate is a soluble salt, right? But the first question you should always ask yourself when you're going into one of these problems is, first, is this salt soluble or insoluble? Because it's going to be a different procedure to determining your ion concentration if something is soluble versus insoluble. So we're starting out with aluminum sulfate, which obviously is going to be soluble because we are in the soluble salt section. But for these ones, you do have to know your solubility rules. If you don't have those memorized, grab the paper that I gave you with your solubility rules on it and literally just keep going through them. Go through them once every night before you go to bed. Try and get these things memorized, because the more you use them, the easier they're going to be for you to memorize, and you do not get them on the AP test. Sad face. All right, so aluminum sulfate we know is a soluble salt, which means it's going to completely dissociate into its ions. So we're going to write out its formula, Al2SO43. This thing's going to completely dissociate, so we're going to draw our arrow like this. And what ions is it going to form? Well, we know it's going to form the aluminum ion, and we know it's going to form the sulfate ion, okay? So what are the charges on these things? Oh my God. Making ionic compounds comes back for the 500,000 millionth time, like I told you that it would. Okay, so aluminum is in group 3, which means it has 3 valence electrons. It is a metal. It's going to lose those 3 valence electrons when it ionizes to become Al3+. Then sulfate is a polyatomic ion, which always has the charge 2- on it. So to quickly balance this out, we know we need 2 aluminums per every 3 sulfates. So here's what our dissolution reaction is going to look like, or dissociation, either one. So to find the concentration for each ion, we start out with the concentration of our salt. We know that our aluminum sulfate had a concentration of 0.10 molar. So how do we find concentration of each ion? We multiply the concentration of the solution by the coefficient for each ion. So our concentration of our solution was 0.10 molar. What's the coefficient for each of these? Well, it's 2 for aluminum and it's 3 for sulfate. So that means our equilibrium concentrations of our salts are 0.20 molar for aluminum and 0.30 molar for sulfate. Boom, boom. Nice and easy. Love to see it. Yay for soluble salts. All right, now we're moving into insoluble salts. All right. So here's the thing. The word insoluble is like kind of harsh, right? Oh, you're insoluble, you'll never dissolve. Bad, finger shaking. But it's not actually true. So even for most insoluble salts, some of it's going to dissolve. So some salt will dissolve in your water. So what we can do is we can figure out how much of that salt will dissolve. So to calculate your concentration for your ions, we're going to use ice tables. We're actually going to use rice tables because I told you that I'm a bigger fan of rice tables, but honestly, it's literally the exact same thing, right? It's do you put the reaction on it or not? And we always will because we are good children who like to remember to look at our coefficients and look at our ratios. So we're going to use rice tables. So KSP solubility product for cobalt 2 sulfide is 5.0 times 10 to the negative 22nd. First things first, let's determine solubility. And then we're going to figure out what's the concentration of each ion at equilibrium. So we know that our solid will not dissociate completely because it is an insoluble salt. So therefore, we're going to use our equilibrium arrows. And we're going to say that our initial concentration is just some value S. We don't know how much we had. But we do know that it will not dissociate right away, meaning we'll have zero concentration of our ions initially. There's going to be some change in our solution where we're going to lose 1S solubility. And then at equilibrium, we won't have any salt left because it'll be completely dissolved by definition. So our equilibrium concentration of the salt will be 0. Each of these are in a 1-to-1 ratio with the cobalt sulfide. So we're going to be adding 1S to each of these for a final equilibrium concentration of 1S. Okay, so our KSP here, our solubility product, is equal to the concentration of our ions. So we've got cobalt 2 plus and we've got sulfur 2 minus. We know that KSP value for cobalt sulfide is 5.0 times 10 to the negative 22nd. So we're going to plug that in here. Concentration of cobalt at equilibrium is S and concentration of sulfide at equilibrium is S. So we can say that this is equal to S squared. Plugging in for your calculator and solving for S, we're going to get S is equal to 2.2 times 10 to the negative 11th molar. So what does this value actually represent? This represents our solubility. So this is our maximum amount of salt that can dissolve. Coincidentally, because the concentration of cobalt and the concentration of sulfide are both equal to S, this also is the concentration of our ions at equilibrium. Oops. Cobalt and sulfide at equilibrium. Because all this is saying is we would plug it back in for these values right here, and we'd get the exact same thing because they're equal to S. So it's our solubility, and it's our concentration of cobalt and sulfide. All right, so this next part B, is asking us what mass of cobalt 2 sulfide would be dissolved in 1 liter of solution, and what mass of cobalt 2 sulfide would dissolve in 500 milliliters of solution. Then we're also going to find out what is the concentration of each ion in 500 milliliters of solution. Okay, so we know that in 1 liter of solution, we can get 2.2 times 10 to the negative 11th moles per liter to dissolve. If we want to figure out the mass of that, we have no units for mass. All we have is units of molarity, which is moles per liter. But molar mass comes back again. So if we can get to moles first, we can get to mass from there. So remember that molarity is equal to moles per liter. We can rearrange this to say that moles is equal to molarity times liters times our volume. So let's start out with our 1 liter solution. For our 1 liter solution, we can solve for moles N. We know that the molarity of our solution is 2.2 times 10 to the negative 11th. This is our concentration. Multiplying it by our volume, we're doing this for 1 liter first. Units cancel, liters, and we end up with N is equal to 2.2 times 10 to the negative 11th moles. Great, now we've got moles. Now all we got to do is convert it to grams. So 2.2 times 10 to the negative 11th moles. We want to figure out how much copper sulfide is dissolving. So our molar mass for copper sulfide is 90.99 grams. Putting this in your calculator, excuse me, what you end up with is 2.0 times 10 to the negative 9th grams. So this is the mass of copper sulfide that can dissolve in 1 liter of water. All right, now let's switch it up and let's do it for 500 milliliters now. So I'm going to actually just very quickly give you these numbers. You can go back and recalculate it later, but what you'll find is that for 500 milliliters, you should be getting 1.0 times 10 to the negative 9th grams that can dissolve in 500 milliliters of water. So what do you notice about these two values? Hopefully you realize that this one is half of this one, and 500 milliliters is half of 1 liter. So what we really are seeing here is that molar solubility and ion concentration in a saturated solution are independent of your volume. Your ion concentration isn't actually going to change. The amount of stuff you have dissolved here is less than the amount of stuff you have dissolved here, because what's actually happening? Take a look at the pictures here. You see more salt at the bottom of this beaker, right? The 500 milliliter beaker. So as you're reducing the amount of your solvent, as you're reducing the amount of water available, less of your stuff is going to be able to dissolve. Your ion concentration doesn't change. It's going to dissolve as much as it possibly can, and whatever's left over stays solid, gets precipitated out at the bottom. So your concentration for these solutions is the same. It's just dependent upon how much stuff you have left over at the bottom. So we can say concentration of CO2 plus is equal to concentration of S2 minus, and we know the value to be 2.2 times 10 to the negative 11th molarity. So here's what you really need to know. This is what you really need to take away. Solubility and ion concentration in a saturated solution, independent of volume. If you just have less volume, more stuff is going to precipitate out of the bottom. You're going to have a bunch more left over, and because your solubility is just based on the maximum amount of stuff that can dissolve. All right, so I want you to do a practice problem now. You're going to basically do the same setup that we did up here for A, but this time you're doing it for copper 2 iodate. Iodate's not one of the polyatomic ions that I actually put on your sheet to memorize, so to help you out, the formula for copper 2 iodate is CuIO3 2. Charge on copper here is 2 plus. Remember, copper is a transition metal, so it can hold multiple charges. And charge on iodate is 1 minus. All right, so work through this problem. Check in with the answer key, and then come on back to continue on the solubility. All right, next section, relative solubility. So what this means is how can we compare the solubility of different substances? So if a solute or different solutes dissolve to give the same number of ions, we can take a look at their KSP values and say that the one that has the highest KSP will also have the highest solubility. So let's practice, see if we can figure out how we can compare these based off of these three salts here. So we got AgI, CuI, CaSO4. So silver iodide will dissolve to produce its ions Ag plus and I minus. Copper 1 iodide will produce its ions Cu plus and I minus. And calcium sulfate will dissolve to produce calcium 2 plus and sulfate 2 minus. So how many ions are we producing in each of these reactions? 1, 2, 1, 2, 1, 2. So we're producing the same number of ions. What that means is because we're producing the same number of ions, we can directly compare their KSP values to tell us which one is most soluble. So this trick, again, will only work if you're producing the same number of ions. So you can't, I want you to be very careful if you try and use this trick. You gotta for sure first make sure that they are dissociating into the same number. So write out your dissociation reactions first. That's always the first thing you should do, okay? All right, so we can start off with lowest solubility and work our way to highest solubility. So the thing that has the lowest solubility means it has the lowest KSP value, the smallest KSP value. So take a look at those three. Which one is smallest? Hopefully you shouted this one, 10 to the negative 16th, much, much, much smaller. So our lowest solubility salt is going to be AgI. This one is worst at dissolving. The least amount per liter will dissolve. So then next up, CuI. And finally, calcium sulfate. This one will have the best solubility of the three, highest solubility. So what happens if your ions, or if your solutes dissolve to give different number of ions? We got to calculate solubility based on KSP. So we're going back to rice tables, baby. All right, so now we're trying to compare bismuth sulfide, Bi2S3, silver sulfide, Ag2S, and calcium sulfide, Cas. Okay, so I'll do the first one, you do the second two, and then we'll see if we can compare. All right, so first reaction, Bi2S, bismuth, oops, I'm missing some subscripts here. Bismuth sulfide, Bi2S, is going to break apart to form bismuth Bi, 3 plus, and sulfide, 2 minus. To balance it out, we need a 3 here, and we need a 2 here. All right, so in solution, this is going to dissolve to give some amount of moles per liter. At equilibrium, we'll have none of it left over, which means our change here is going to be minus S. To start us off, we have no ions present, so concentration of 0. All right, we have a 2 in front of our bismuth here, which means we are going to be adding 2S in our equilibrium. And for sulfide, we're going to be adding 3S in our equilibrium. So our final equilibrium concentrations, bismuth will be 2S times, and sulfur will be 3S. So there's our final equilibrium concentrations. Now we got to calculate out what the solubility actually is. What is the S value equal to? So start out by writing our KSP. We know that KSP is equal to the concentration of our ions. So we have Bi3 plus squared, because we have a coefficient of 2. And sulfide 2 minus raised to the power of 3. This is a coefficient because of the coefficient of 3. So now let's start plugging things in. We know that our KSP for this is 1.1. Oops. 1.1 times 10 to the negative 73rd. Oof, yikes. That thing is small. So our concentration of bismuth ion at equilibrium is equal to 2S. Do not get it confused. You are not accounting for that 2 as a coefficient when you're raising it to a power of 2. Remember that the law of mass action, when we first learned about equilibrium constants, told us that by definition, whatever you have as a coefficient, you're going to bring up as a power in the equilibrium constant expressions. And the exact same thing is true here. So our solubility is equal to 2 times S based on the stoichiometric coefficients, but you still have to square it because of the definition of law of mass action. So then for sulfide, we've got 3S that we're going to cube. All right, so bring this down, 1.1 times 10 to the negative 73rd. 2S squared is equal to 4S squared. 3S cubed is equal to 27S cubed. Okay, still multiplying things in, 1.1 times 10 to the negative 73rd. All right, when you multiply variables with exponents, you can add the exponents together. So we have 4 times 27, which gets us 108. S squared times S cubed is going to get us S to the 5th. So now we have to fifth root something. Talk to me if you don't know how to do this in your calculator. I will show you how to do it later. For right now, I'm going to give you this answer because the other two do not have to do fifth roots. So for this first reaction, S, our solubility, is equal to 1.0 times 10 to the negative, 15th molar. So this is our solubility for this reaction here. Okay, I'm going to let you do the other two on your own. So I want you to pause the video, figure out the S value, the solubility for silver sulfide and for calcium sulfide. Check in with the answer key and then come on back, okay? All right, so after you've done these, what you should have found for solubility for silver sulfide is 3.4 times 10 to the negative 17th molar. And for calcium sulfide, 9.2 times 10 to the negative 23rd molar. Okay, so here's our 3S values. Now what we can do is we can compare these together to figure out which will have the lowest versus the highest solubility. So now we're looking at our S values because S is solubility. This number is clearly the smallest, which means that calcium sulfide is going to have the lowest solubility. All right, going from lowest to highest, what's the next number that you see? Hopefully you said silver sulfide. Silver sulfide's 10 to the negative 17th. That's the next smallest number. So silver sulfide is going to be our next, our middle of the road solubility, which means that bismuth sulfide, Bi2S3, is going to have our highest solubility. So this process that we just went through will work for, like, if you wanted to do this practice problem up here, the AGI, the CUI, and the CaSO4. It'll work no matter what. If you have something that results in different amounts of ions, like you're resulting in 5 ions in the first one, 3 in the second, and 2 in the third for these ones right here, you have to do this process by calculating out the solubility using Rice tables. It's the only way that you can work on comparing. Okay, next up, common ion effect, moving forward. So what is the common ion effect? Common ion effect describes the decrease in solubility of a compound that results from dissolving the compound in a solvent that contains one of the ions in the compound. So that's kind of a mouthful, right? So let's say that instead of taking a compound and dissolving it in water, you take a compound and dissolve it in some other solution. If those two compounds share an ion, they have something in common, then the common ion effect will go into place. So let's see what that looks like numerically. So consider the compound calcium fluoride with a KSP of 3.9 times 10 to the negative 11th. In water, the solubility of calcium fluoride can be calculated using an ice table. So we have calcium fluoride. It's going to dissociate into its ions, Ca2 plus and F2 minus. So if we know we're starting out with solubility S and we have no concentration of our ions, using our stoichiometric coefficients, we know that we're going to add S for our calcium and we're going to add 2S for our fluorine. We'll have no salt left over at the end. We'll have S molarity of calcium and 2S molarity of fluorine. All right, so our KSP value, or our KSP, is going to be equal to our concentration of our ions. We have calcium and fluoride. Fluoride needs to be squared. In water, we know the KSP value to be 3.9 times 10 to the negative 11th. This is going to be equal to S for our calcium and 2S squared. Oof, caught myself. 2S squared for our fluoride. So this is going to be equal to S times 4S squared. So what is this really equal to? 4S cubed. So 3.9 times 10 to the negative 11th is equal to 4S cubed. Dividing by 4 and cubed rooting, what we're going to end up with is that our solubility is equal to 2.1 times 10 to the negative 4th molar. All right, so this is our solubility in water. Now let's say we're trying to compare it, the solubility of calcium fluoride, in moles per liter, if we're trying to dissolve that calcium fluoride in a 0.1 molar solution of sodium fluoride. It's no longer dissolving in water, we're dissolving in sodium fluoride now. So what do these things have in common? We got calcium fluoride and sodium fluoride, which means that fluoride is a common ion. So we're starting out with some amount of calcium fluoride, right? We're starting out with no calcium ion present still, but sodium fluoride is an aqueous salt, a soluble salt, which means that there will be some fluoride ions already present in the solution we're trying to dissolve the calcium fluoride into. How much? Well, there will be 0.1 much. There will be 0.1 moles per liter of sodium fluoride. Because when this thing dissolves, NaF, it's going to dissolve into the Na and F ions. So if we have 0.1 molars of sodium fluoride, we have 0.1 molar fluoride ions. All right, so then let's go back to our change here. So we're going to lose S amount of calcium fluoride, resulting in nothing left at equilibrium. We're going to gain S amount of calcium, resulting in S amount at equilibrium. And we're going to gain 2S amount of fluoride ions. And at equilibrium, we still have that 2S amount, but we also have to take into account the fact that we had 0.10 to begin with. So let's set up our KSP. KSP is going to be equal to the concentration of our calcium ions times the concentration of our fluoride ions squared. This math gets a little bit complicated if we're trying to add in this big mouthful right here, right? So what we're going to say is we're going to assume S is small. Just like those assumptions that we made with our equilibrium calculations in the earlier lesson, we're going to make an assumption here to say that S is a small value to make our math work out better. We can always do checks as well for these assumptions to make sure that they actually work. If you forgot how to do that, go back and watch that other video or look back at our other lesson that talks about how we can make assumptions and when they're valid. All right, so our KSP for calcium fluoride is 3.9 times 10 to the negative 11th. Our concentration of calcium is just S, and our concentration of fluoride, since we're assuming that S is small, we're going to take off that last factor, that 2S, and we're just going to say 0.10 squared. Okay, so what we are assuming now is that, or what we're going to do now is, let me just rewrite this. We have 3.9 times 10 to the negative 11th. When we take 0.1 and we square it, we get 0.010, and then the S just remains as S. So solving for S, we divide out by 0.01, and we end up with the value 3.9 times 10 to the negative 9th molar. So compare these two values. We have 2.1 times 10 to the negative 4th versus 3.9 times 10 to the negative 9th. So this number is significantly smaller than the one that came before it. What does this mean? It means that calcium fluoride is not as good at dissolving in a solution of sodium fluoride than it is in water. Why? Because there's already fluoride ions present. There's already dissolved F minus ions. So it has to take into account the fact that we can't dissolve a bunch more stuff that where we're trying to add more fluorine in. There's not going to be any space for it. So this can also be explained using Le Chatelier's principle. So let's take a look at this right here. If there's already dissolved fluoride ions and we're trying to add more to it, we're effectively increasing the concentration of F minus by trying to force more stuff to dissolve. So what's going to happen to this equilibrium? Boom. Shift towards salt. It's shifting left. It's shifting towards the reactants, which in this case is our salt. So if we're shifting towards making solid salt, less stuff is going to be dissolved. So just as a reminder, in solution, already, what is that letter? Already have dissolved F minus ions. So what you really need to know, common ion effect, if you are trying to dissolve a salt in something that already has a common ion with something in that salt, it is going to have a lower solubility. It is going to be less effective at dissolving because there's already dissolved ions in that solution. So you take a chance and practice this exact setup now with silver chloride. Check in with the answer key and come back for more solubility. Okay, here we go. Solubility reactions. So luckily, you guys will already be good at these because you've already seen them, you've already done them. Solutions of soluble ionic compounds can react. So you have aqueous ionic compounds, two aqueous ionic compounds, and they're reacting to form an insoluble precipitate. Two aqueous compounds form something that's aqueous and something that's solid. What type of reaction is that? Everybody screams double replacement reactions. So you're already good at these because you've already done 750 million thousand of these. So these double replacement reactions can be written in three forms. You got the formula equation, which is basically just your balanced equation with like states of matter with solid and aqueous. Then you have your complete ionic equation where all ionic compounds are dissociated. Oops. So everything that's ionic, you break it up to write it as its aqueous form with its ions. And then you have the net ionic equation. So for these, remember that if you have identical ions, they get canceled out. So you basically are just writing like what's responsible for making your precipitate in the net ionic equation. And then the ions that don't participate in your reaction, the ones that you cancel, the ones that are left over, we call them spectator ions. So you already know how to do these. So I left these two as practice problems for you. So try to work those out, check in with the answer key, make sure you still know how to write a net ionic equation, and then come on back for what you all will probably scream at me for tomorrow when you see me. Yay. Okay, pause and come back. All right, determining if a precipitate will form. So, other than just knowing solubility rules, the problem is things can be slightly soluble, or things can have their solubility change depending on how much solvent and solute you actually have present. So what we can do is actually mathematically calculate if a precipitate will form from our solutions. So if we have two solutions and we mix them, a precipitate's only going to form if your ion concentrations are high enough. So to determine if your ion concentrations are high enough, we're going to use Q. We got to calculate a Q value. So remember that Q values come from initial concentrations. It essentially just means you're not at equilibrium. It's used to compare to your K value. So when your two solutions are mixed, the concentration of each ion that could lead to a precipitate must be calculated by considering the total volume of your solution. What this essentially means is a solution dilution. You're mixing two things together. They're going to together have a new volume, a new total volume. So you're essentially doing a dilution. So when you calculate these things out, if you find that your Q value is greater than your KSP value, what that means is your ion concentrations are high enough for a precipitate to form. You have too many ions in solution, so some of them have to come out of solution by making a solid precipitate. Alternatively, if your Q value is less than KSP, your ion concentrations are not high enough for a precipitate to form. What that means is you have too few ions in solution. They're not going to come out as a solid because there's a few enough of them that they can stay dissolved in your solution. Okay, so let's do an example. Will a precipitate form if you have 20 milliliters of 0.01 molar calcium chloride and you're mixing it with 20 milliliters of 0.008 molar sodium sulfate? Calcium sulfate has a KSP value of 6.1 times 10 to the negative 5th. Okay, so both these salts we're dealing with, calcium chloride and sodium sulfate, are soluble salts, which is really nice for us because it means we can get the concentration of those ions pretty quickly. All right, so if we think about this as a double replacement reaction, we have calcium chloride and we're trying to react it with sodium sulfate. So what's the potential precipitate we could form? Gives you like a very large hint here in the sense that it gives you the answer. Can't make you can't make sodium chloride because that's a soluble salt. Anything with group 1 ions is always soluble, so that's going to stay in solution, which means the precipitate we're looking to form is calcium sulfate. So let's start out with calcium chloride. We have calcium chloride. This thing is a soluble salt, so it's going to break up into its ions Ca2+ and 2Cl-. Our initial concentration of our salt is 0.010 molar, and since I only care in this reaction about the calcium ion. We don't care about the chloride because we know it's a spectator, so I'm not going to bother with calculating its concentration in solution. So I only care that I'm going to have a 0.010 molar solution of calcium ions when this dissolves. Remember, because these are soluble salts, we can use that very first thing we learned 700 hours ago at the beginning of this video, that the concentration, we just have to multiply the initial concentration of the salt by the coefficient of our ion. All right, so next ion we're taking a look at, sodium sulfate, Na2SO4. This thing is going to dissolve to break apart into its ions, 2Na+, plus SO4, 2-. So again, I don't care about the sodium. It's going to be a spectator ion. It's not responsible for my reaction. So what I know is that I have a 0.0080 molar solution of sodium sulfate. So what's my concentration of the sulfate ion? 0.0080 molar, because we're in a 1-to-1 ratio. All right, so remember that because we're going to calculate a Q, we care about the total volume of our solution here. So we started with 20.0 milliliters of the calcium chloride, and we're adding to it 20.0 milliliters of sodium sulfate. So our total volume is 40.0 milliliters. Total solution volume. All right, so we're essentially doing a dilution, right? We're adding these two things together. What's the concentration of our new stuff gonna be? Our new concentration in our new volume. Okay, who remembers the dilution formula? Oh, I hope we all do. M1V1 is equal to M2V2. What we're essentially solving for here is what is the new concentration of our calcium ion and the new concentration of our sulfate ion when we mix these together. So now we have a 40 milliliter solution. So we're going to do this twice. First, we're going to do this for calcium. How can I find my new concentration? Well, let's rearrange this equation. M2 is going to be equal to M1V1 divided by V2. What's my initial concentration for calcium? 0.010 molar. What's my initial volume? 20 milliliters. But remember, I'm working with molarity, so I really should be doing things in liters. So that's equal to 0.020 liters. My new volume of solution is 40 milliliters, so 0.040 liters. Units cancel, liters and liters. And I'm left over with my molarity. When I plug this into my calculator, I end up with my concentration of calcium ions in my new solution being 0.0050 molar. Great. Now let's do the sodium. All right, so concentration of our, sulfate. Let's do our sulfate ions. So our sulfate concentration started out as 0.0080 molar, and I had 0.02 liters of it. My new solution volume is 0.40 liters. So again, units cancel, yay. And when I plug this into my calculator, I end up with 0.0040 molar solution. So this gets our new concentration of our ions in solution, which is great for us, because now what we're going to do is figure out our Q value. So these two ions are going to come together to form calcium sulfate. When in solution, remember, if this is going to be our insoluble salt, some of it's going to dissolve a little bit. So this thing can still break back down into Ca2+ and SO4 2-. So the KSP will be concentration of calcium times concentration of sulfate. But we're going to calculate a Q value. So it's set up the exact same way. It's just we use our initial concentrations instead. So in our new solution, we're going to say our Q is equal to our concentration of calcium, 0.0050 molar, times our concentration of sulfate, 0.0040 molar. And when we plug this into our calculator, we get a Q value of 2.0 times 10 to the negative fifth. So let's compare these things. 2.0 times 10 to the negative fifth versus our KSP for calcium sulfate, which is 6.1 times 10 to the negative fifth. So here's KSP, here's Q. Which one's smaller? It's the Q value. They're both 10 to the negative fifth, so now we have to look at the numbers. 2 is smaller than 6.1. So Q is less than KSP. Let's consult what we said above earlier. If Q is less than KSP, if Q is less than KSP, then our ion concentrations are not high enough for a precipitate to form. So what does this mean? A PPT will not form. So we are not going to make a precipitate. We have too few ions in solution. They're going to stay dissolved in solution. There will be no solid that comes out at the bottom. All right. Let's do another practice. Let's have you pause the video and work through just part A for right now to determine if a precipitate's going to form by finding the Q value and comparing it to KSP. When you're done with that, come on back to the video and we'll work through B together. Okay, so what you should have found is that Q is going to be greater than KSP, which means, yes, a precipitate will form, which is great. Part B is now asking, after that precipitate forms, which you should be looking to form magnesium fluoride, MgF2, what will the concentration of the ions magnesium and fluoride be in solution? So in order to calculate this, we have to figure out which one's going to be our limiting reactant, which one's going to be left over as ions in solution as excess, because that'll help us figure out how much stuff we're going to have left over. So bear with me. This problem's going to be a little long. Write small, save yourself some room, take a deep breath. If you have not taken a little pause during the duration of this video, do that and get up and stretch, put yourself in a good mindset, and come back saying, yeah, Miss Lambert, I can do this problem with you, because it's going to be great. Okay, here we go. All right, so here is what we need to start out with. We have to start this problem to calculate the concentrations of magnesium and fluoride at equilibrium by calculating the number of moles of each ion. So start by finding number of moles of each ion. So one ion is going to be limiting, completely consumed, going into making our precipitate. The other is going to remain excess in solution. All right, so we know that we are working with this reaction right here. Our magnesium ions are reacting with our fluoride ions, and we are making the solid precipitate magnesium fluoride. I'm going to move this over a little bit to give ourselves some more space. So we're going to make ourselves a little table. So here's our reaction. we're going to now make ourselves our starting here is going to be our initial number of moles. So how much stuff are we starting with? Okay, so from the problem above, what you should have found was in your initial solution, you had 0.01 molar magnesium from the magnesium nitrate, and you had 150 milliliters of it. So if we want to find an initial number of moles, and we know concentration and we know volume, we can once again rearrange this equation to get moles is equal to molarity times liters. So for magnesium, we started out with a concentration of 0.100, and we had 150 milliliters of it, which is 0.150 liters. I'm not going to put in units for right now, which is, I know, bad, Miss Lambert, but I want to try and write small. So when we multiply these things together, we end up with 0.00150 moles of initial magnesium ions. Okay, so now let's do the same thing for fluorine. So for the fluoride ions, we started out with a concentration of 0.100, and we had 250 milliliters of it, so 0.250 liters. Put this into our calculator, and we end up with 0.0250 moles of fluoride ions. So remember, if we're trying to figure out which one's our limiting reactant, which one's going to run out first, we can only compare these things in moles using the stoichiometric coefficients. So magnesium, we're just using 1 mole of. Fluorine, we need 2 moles every time. So I'm going to take my initial number of moles here, and I'm going to divide it by 2 to compare how many moles I have in like a 1-to-1. So when I divide this number by 2, I end up with 0.0125 moles. And comparing how much magnesium I have versus how much fluoride I have, I clearly am going to run out of magnesium first. That thing is smaller. So that means that magnesium equals our limiting reactant, which is good news for us because we know that when this thing produces the solid precipitate, all of the magnesium is going to go into making the solid and will be left over with no moles at the end. So this is basically like a BCA table that we're making, but I'm just doing some of the work for the limiting reactant inside of the table. The other thing is we want to calculate magnesium ion and the fluoride ion concentration, which means we literally do not care about the magnesium fluoride here. Don't do anything with it. No one cares. Sorry, magnesium fluoride, you are the weakest link. No one matters. Okay. So we got our initial number of moles here for magnesium and for fluoride. Now we need to find our change in moles. Change in moles. How can we do that? By knowing our final number of moles. We know that our magnesium is going to completely run out. There's going to completely react to just produce our solid precipitate. So at the end, we know we'll have 0 moles of magnesium ion. So we're going to lose all 0.00150 moles of it in this reaction. So because magnesium and fluorine react in a 1-to-2 ratio, we are going to lose 2 times 0.00150 moles in our solution. For every 0.00150 moles that react of magnesium, we need double that amount of fluorine, which means we're going to use 0.003 moles of our fluoride ions. So how much will be left in solution afterward? Well, we started with 0.0250 moles. We're going to use 0.0030 moles. So we're going to have left over 0.022 moles after this reaction has run its course. So here's our remaining F minus. LR, so none left. Okay, so this is our number of moles of each of these things that's left over after we make our precipitate. But keep in mind, our precipitate is said to be insoluble, but we know that insoluble salts can undergo dissociation to release some of those ions back into solution. So we're not done with this problem to find our concentrations at the end. So because some of this precipitate is going to undergo dissociation, we now have to figure out the concentration of the ions using our Rice table. So let's go over here to start our next section. So some of the precipitate that is formed will undergo dissociation. So our reaction, we've got our magnesium fluoride that's going to break apart into its magnesium ion and its fluoride ion in solution. We are starting out with some amount of magnesium fluoride that we call S. We know we're starting out with no magnesium ions in solution because all of it went to forming the precipitate in the first place. And we are starting out with 0.0550 molarity of our fluoride ions. Oh, sorry. I guess I should tell you how I got that number, huh? I was just realizing now that I didn't do that step. So how can we figure out how much fluorine we have? Well, let's go back down here. So to find our initial concentration of our fluoride, we know that we're looking for moles per liter. So how many moles do we have? 0.0220. And what's our total volume of solution? Well, we had 250 milliliters of the sodium fluoride and 150 milliliters of magnesium nitrate. So add them together and you get 400 milliliters. So we have 0.400 liters of solution. So when we do this, this is how we end up with our concentration of our fluoride ions. Because that's the amount of fluoride that's still dissolved in our 400 liters of solution. So that's why it's our initial over here. Sorry, forgot to do that step real quick. Okay, so here's our initial amounts. Now we got to calculate, or we got to determine our change and find out what we're going to have at equilibrium. So by definition at equilibrium, we should have 0 of our salt dissolved, which means we are going to lose S amount of it. What's its solubility? That's what we're going to find out. So we are going to gain some amount of magnesium ions back, and we're going to gain back twice the amount of fluoride because of the stoichiometric coefficient. So at equilibrium, we'll have S magnesium and 0.0550 plus 2S fluoride. So again, that's going to make this little deal right here is going to make our math a little complicated. So we're going to make an assumption. Assume S is small. Small enough that we can basically say it's negligible and count it as 0. All right, so if we're assuming that's small, we're going to say our KSP is equal to the concentration of our magnesium times the concentration of our fluoride squared. Plugging this in, we know that our KSP for magnesium fluoride, we can find back up in part A, is said to be 5.16 times 10 to the negative 11th. Concentration of magnesium is S. Concentration of fluoride, assuming S is small, is 0.0550 squared. Squaring that, dividing that out on either side so we can solve for S, I'm just going to skip a couple algebra steps, gets us 1.71 times 10 to the -8th molarity. So here is the solubility. So finally, after all this work, what we can figure out is the concentration of our magnesium and our fluoride ions in solution. So therefore, finally, our concentration of Mg2 plus is equal to S, and we said our S value is 1.71 times 10 to the -8th molar. Our concentration of the fluoride ions is equal to 0.0050 or 0.550. Yeah, I think I said that wrong. Plus 2S, so 2 times 1.71 times 10 to the -8th. When we plug this in our calculator, this term is so insignificantly small that rounding to sig figs, we end up with 0.0550 molar. So here are our equilibrium concentrations. Excuse me. So here are our equilibrium concentrations of each of those ions. And now we take a big, deep breath, and we are done with the problem, and we are done with the worksheet, and we give ourselves a pat on the back, and we go to sleep. Bye, everybody.